So my name's Chris. I'm a PhD student at Laurentian University in my second year, and my advisor is Dr. Richard Smith. And today I'm going to be sharing some preliminary results on gravity and seismic tomography inversions in the Sturgeon Greenstone Belt area. So we could probably guess from the title that I'm going to be looking at the upper crust in this area. And the challenge from that is that in a survey designs for like a lot of crustal scale surveys, it's really difficult to image these upper 10, upper 5 kilometers of the crust, and it's for a multitude of reasons, mostly because of the remote nature of them and the inability to put very 3D type surveys in these places, and then that leads into the physical limitations of each method. And to be more specific, in the Metal Earth project, I can bring up 3 examples. First would be with the reflection seismic images. They're found to be, in general, acoustically silent in the upper 5 kilometers. And this is due to the brittle nature of the crust and steep angles that you would find in that layer. MT, in general, can be. However, it requires a more high resolution survey, and not all lines have a R2 line. So for instance, the Sturgeon is more geared for the lower crustal upper mantle imaging. And the final example of our data set includes gravity, which is sensitive. However, as Fabiano was explaining in our previous talk, there is uncertainties and unreliabilities to using gravity data if you don't incorporate any external constraints or really strong priors into your modeling before calculating them. So the Sturgeon Greenstone Belt is located in the Western Wabigoon area, and the Western Wabigoon is located in the Western Superior Province, and also this area is along the western border of Ontario. And on this map, I'm just showing the various transects that fall within this area. And the important one to note is line 331, which is the Sturgeon transect, which crosses the Greenstone Belt itself in its middle, but also the boundary between the Winnipeg River and the Western Wabigoon sub-provinces. As well, I'm showing some of the legacy data sets that I'll be using, and I'll describe as I get to that methodology, but that's how it sits in relation to our Metal Earth line. And that's the lithoprobe wide angle seismic line. And this just zooming in to the Greenstone Belt, and just showing some more of the data sets and the lithological interpretation in this area. So you can see that the Greenstone Belt is mixed with some mafic and felsic intrusives, and it's bordered on both the north and south ends by granitic and plutonic provinces. The Winnipeg River sub-province is to the south at a boundary about here. And the blue dots are the GSC gravity stations, and the black dots, which are forming a line in this image, are our Metal Earth gravity stations. And that same line has our reflection seismic receivers on there. And then also showing some more of the wide angle shots and receivers in the area. I'm now borrowing an image here from one of our colleagues that is providing an interpretation of the reflection seismic section on that line. So on the top is the map, and showing the CMP line, which is closely approximates our transect, and then down here the section itself. And so this is showing the reflections, and the area that we'll be talking about today is in the South Sturgeon area. So I'm limiting the discussion to this spot here in the middle, and the upper crust of that, everything above 10 kilometers. And you can see that it contains some regional faulting, the South Sturgeon fault zone and the Sturgeon Lake fault zone, which dip approximately to the northeast. And in the broader scope, you have the Winnipeg River terrain underwriting the Western Wabigoon terrain. As far as geophysical imaging of these areas go, we could look for the mineralogy in question. And in this area, there are a lot of volcanic or VMS deposits. And in these, they'll have physical property contrasts in terms of density and then their elastic properties. And this is particularly true in relation to their host rocks, whether it be a plutonic or greenstone belt. They'll have a very high density or or a good range of elastic properties, which you could use gravity imaging or various seismic techniques to try to image. So I've been using the inversion methodologies, and this just a quick primer on that. Inversion is a cell-based approach where you try to estimate the physical property model as a bunch of discrete units of constant value from the data set in the area. So, for instance, we can estimate density from our gravity response field, and it's just done by setting up a linear system, and essentially we're working from the measured data back to our model and trying to estimate a vector of the model parameters using some sort of relation that defines that link between the data and the model space. This is easiest explained with gravity data. So here's just a simple cartoon, and on here I've drawn an anomaly that would be considered more dense than the surrounding area, as well as some stations on the top here that would be measuring that gravity data and then showing what the pull of gravity for this may look like. And this relationship is based on Newton's law of gravity. However, in this sort of approach, while you can get really high resolution in imaging this sort of structure if you had enough sensors, there is inherent non-uniqueness to this. And what I'm saying is that if you could reconfigure this estimation of this anomaly in many different ways or different depths and get the exact same data response. So often gravity inversion modeling requires a priori information or really strong constraints to get something reliable out of it. My second physical system I'm talking about is refraction tomography. So again, just another cartoon, and this is somewhat more complex. So in this case, we would have an energy source, and it's going to radiate energy through our model and be picked up by the receivers, and then we can guess the arrival times of the waves of interest. And they could either dive through or they could hit a layer and refract along it, depending on the contrast and velocity. More complicated problem, and that's highly nonlinear. Not only do you have to estimate the model parameters to get the correct estimation of your observed data, but you also have to estimate the ray paths that go through it. So it's you have to estimate one and then the other. So it's sort of a cyclical process. And what we're trying to achieve is to figure out, a bunch of lengths of this ray path through each model, and then you can estimate the slowness or seismic velocity of that cell. It is very quick and inexpensive computationally. However, it has a few limitations of its own. While it could be really good at discriminating different depths of layers, it is limited to simplified models, at least simplified starting models. And for instance, like a layered approach like this. Also, you would have to consider that URays need to penetrate the cells in order to determine, what this property is. So if you got sparsity in between areas, then you can't say much unless you provide a smoothing over that. So one way to kind of work around these two limitations is to basically combine these inversions in some sort of scheme. The most easiest is to use multiple inversions, and just to be aware as an interpreter of the strengths and limitations of each. And that's just like a side-by-side approach like this. But a little more linked, I would say, is a cooperative approach where you can take the output of one inverse model and feed that into your second one, and that's called the cooperative approach. And the more strong link is what's called joint inversion, which is the methodology I'm talking about today, where you have a link between the models which are inverted simultaneously. And this link could be structural similarities or similarities, like empirical similarities between the physical properties of each system. And the advantages of that is that you can handle noise better between each, and you can overlap in areas where, there's some are not sensitive to each other. So I'll just explain, or just show my preliminary results that I've got by applying this approach in the South Sturgeon greenstone belt. So, excuse me again. So this is the area of the transect, and I've got two sets of results essentially. So the first, I've divided into what I've called the transect scale. And then afterwards, I'll show you the regional scale where I bring in that legacy data set. But first, we'll talk about the area closer to the metal earth line. And the data that's involved in this is all metal earth data and GSC gravity stations. So we're using the first P wave arrivals from the Firosites data that we have collected along the R1 line, and the gravity station data with the Bouguer corrected, and then the filler in the 3D area, because this is a 3D model that we're making, is just to add in the GSC data. And as far as the seismic data goes, I had to pick some new first arrivals, and that's in order to try to encourage the overlap between the seismic and the gravity models. So as I was showing before, the depth of your ray path is pretty much determined by how far of offset you have between your source and your receiver. The further that you can define that, the deeper the rays would go. I think after working through this, I've determined that you would get about 1 kilometer per 20 kilometers of offset of picking. So in some cases, I was able to pick up to 40 kilometers. In general, between 23, 20, and 30 kilometers at most for the lines I picked. It's also a very onerous task. It takes a long time to do, and this is just initial preliminary work. So what I did is I picked every 10th shot gather, just so that I can get through the whole line in one go, or I plan in the future to revisit and pick at a higher interval. So as every shot is 50 meters apart, we essentially have a sample spacing of 500 meters in this case. In terms of the model space, I discretize this into rectilinear grid along that by rotating the system into a straight X and Y plane, and brought it to the level that I could on my workstation. So I discretized into 150 cubic meter blocks and to a depth of 11 kilometers, which is basically determined by the gravity expected result. Then as far as inversion, I calculated a initial model using the slope intercept method and came up with an optimal 3-layer velocity model. And that's over the first 10 kilometers. And for the density model, I used a simple relationship to estimate what a starting density model could be using Gardner's relationship. The inversion I carried out in Tomo Plus by Geotomo, and it contained 3 bodies of work. The first was to just do a 1 plane unconstrained gravity inversion, the second, 1 seismic tomography, and the third to fuse the first 2 using a joint technique, a joint seismic gravity modeling, and then to compare the 2. For that, the link between the models, I chose structural coupling link, and that's the cross gradients approach of Gallardo and Mayhew. And this just uses the cross gradient operator, which is the cross of the spatial gradients of each model. And you take that covariance and minimize your misfit in accordance to that. And in order to try to quantify how the effectiveness of doing this, I use this to apply statics corrections, which are corrections to the travel time delay caused by the weathering layer, the topmost part of the crust, essentially. And these kind of delays can be estimated using tomography and then incorporated to essentially fix the reflection images where there could be some noise that would disturb reflections. And again, I did this in Geophysics by Geotomo. And I evaluated the effectiveness by looking at shot gathers in the area of the South Sturgeon greenstone belt. So here's just the misfits for the various trials that I ran. So in the first, I'm just showing the comparison of the joint and the single property seismic tomography inversions. And showing the single in red, you can see that it did not converge to as low of a misfit as when I applied the joint technique, where the joint was considerably lower, down to about 10 milliseconds of difference. However, the reverse is true with the gravity modeling. where I actually got a much lower fit by applying just a plain unconstrained gravity inversion than I did by bringing in the joint methodology here. I think the reason for that would likely be overfitting of the data to the model in this case, and you can see that in the printouts here of my model. So just the plain gravity inversion is shown here on the bottom, and above that is the P-wave refraction tomography model. And one thing I want to point out while you're looking at this now is that the depths here are different. So again, the tomography model is limited by the depth that the rays can penetrate. So here, just to make it viewable, I've put this to about 3 kilometers of depth. Was the gravity inversion I'm showing here to depth of 10 kilometers. Now here's the result after performing joint inversion of these same 2 models. And the main difference here I can show with relation to the South Sturgeon greenstone belt, where I'm focusing on this interpretation right now. And I've just kind of shown here that we can, with the refraction imaging, we can pretty clearly see the depth of the South Sturgeon fault zone. And in comparison to the previous gravity model, which was more concentrated into the localized anomalies, this one appears more smoother, and the boundaries appear to me to start to represent the dip of the geology as we understand it, and to, of course, match in between them because they were structurally coupled. And there's just one more view of that gravity field. I'm just showing it now, looking on the other direction of that line, but now in 3D. So this is looking east. That's the easiest way to see it. So the South Sturgeon zone is here, and here's the dip between the Winnipeg River and the Western Wabigoon subprovince, as imaged by the gravity method. And as for the tomostatics, I plotted the shot and receiver delays over as they're seen over the transect, and higher colors in delay, so more error, are shown here in yellow. And I found that most of them are actually located down here over the Winnipeg River to Western Wabigoon boundary. There's also a small bit here within the structural deformation zone between these regional faults that come through the area in the South Sturgeon greenstone belt. I examined shot number 431 for its effectiveness. So that's right here on the boundary between that greenstone belt and this continent. So that's what I'm showing you here. I picked out one shot gather, and I'm applying that tomostatics to correct it. So here's just with no statics corrections. So when you're looking at this shot gather, you can see that there is in the first P wave arrivals a bit of undulation that they don't line up in the way that you would expect. And in this reflection, which I'm zooming in on the right here, there is a slight hump in the middle where you would expect a hyperbolic move out in a reflection. Here, if you were to perform NMO and various migrations, it may not line up, and when you stack it, there could be destructive interference and damage the appearance of this reflection in your final stacked image. So applying statics does help correct this. So just using the single property velocity model to apply corrections, you can see the difference right away in removing this hump, this delay in our travel times to make it more smooth and to improve that image quality. So I can just cycle back one more time here. If you keep your eye on the purple arrow, and as I move forward, you could tell that they've lined up, the P wave arrivals have lined up from doing this. Now, the next one I'll show the joint result, where I've used the gravity data to help calculate the statics. And I believe that it is improved again on this. So compared to the previous result, again, if you follow the purple arrow at the top, the P waves have lined up just a little bit more from this. And in the reflection on the bottom, to me, it appears to be more hyperbolic than it was before. So my second method and results is now on the broader scale of the area, where I'm using the lithoprobe wide angle refraction survey that was done. So this is again panned out to the whole Western Wabigoon subprovince, and I'm showing on this map here the shots and receivers from these two lines. So when they collected this line, they did it as two 2D profiles. So you would have your north-south profile with a string of shots and receivers along this, but you also had your east-west along this way to get two 2D images that crossed each other here, pretty close to the Metal Earth transect. But what they also did when they collected this data is they collected broadside shots and did fan shooting. So these yellow dots I'm showing here are the broadside receivers. So what I'm saying is that in this north-south profile, when they're collecting it, they had these receivers on at that time in a smaller survey. So your shot energy would crisscross through essentially where our transect is, like this. And likewise, when they did the east-west, our shot energy would crisscross through this. Doesn't give like a totally 3D survey, but it does give a pseudo 3D aspect to this area which we can use. And interestingly, given the location of where the Sturgeon transect is situated in the intersection of these two lines, I mean, sort of like an end-on intersection with these ray paths. So in areas where they intersect more, I anticipate that we could use this data to help with constrain the gravity data deeper depths than we could with just the Metal Earth shots, which were limited to about 2.5 kilometers. So in this, I picked the first P wave arrivals. They're of a substantially bigger offset. They can go up to about 300 kilometers, and it's about 45 seconds of delay. And it's a much bigger model. I have to include all the areas out here as well. So I used an adaptive grid. Areas away from the Metal Earth area have very big cell spacing, as we're not going to be imaging anything in there. And then refine that down to cells of 1 by 1 by 500 meters deep. And that was just taking it to the level of the memory I had available to calculate this, at least in this initial trial. And I took the depth to 18 kilometers in here. And again, I used Geotomo to do this inversion. I started with a 2-layer initial model for the crust. The offset in this case doesn't allow for any imaging the moho. It's too close of offset. So we're just looking at about 18 kilometers of depth. And I just performed the seismic tomography in this case. I haven't been able to do the joint inversion yet, but that is coming in the future. So here's just a depth slice of that model that I ran. And obviously here's the Sturgeon line, and just showing the P wave velocity in that area. And keep in mind that everything out here is pretty much, it has no ray paths going through it. The only place that it has data determination would be up in here. And it increases as you get towards the apex. So this is what I got after 9 rounds, but what I'm really interested with in this preliminary trial is the ray counts, more so than the velocity model. And the ray counts can tell me where I can get some input, some information from this, where the Metal Earth line is. So this little image here is just looking northwest as this line here, as if you had rolled it onto here. And these little colors here tell you how many rays pass through each of these cells in here. And you can kind of just tell when you look at this that up in this end of the survey, up here, where the offset is shorter, you're getting less deep arrivals, and they're more frequently. And as you get down here to where the South Sturgeon greenstone belt is, they're actually they're quite a bit deeper. They're almost 10 kilometers, and they're quite a bit more sparse. And this is just another look at that. Just showing in 3D. I'm just replotting that and looking west now, and just bringing in that model space from my first result, just to show where they intersect and where we can try to synthesize this data. So the black lines here, these heavy black lines, are just the model domains from my first results, the joint results I showed earlier. This gray plane that I have spliced through here is the scene P line from our seismic survey. So we can see right on here where the ray paths intersect this, and count how many intersections we get. And so just to wrap up, so in the transect scale modeling, I found that the joint approach was helpful for calculating statics. And I believe that if I continue with this, pick more first arrivals, I could improve the reflection images by incorporating the density information alongside the first arrival information. And as far as the density model goes, It's to me, it appears to show a more reliable dip at the contact of the Winnipeg River and the Western Wabigoon sub-provinces. The results in this, of course, are limited by the ray penetration depth of the metal earth line. And in terms of the regional scale modeling, this is focused on the lithoprobe data. I found that we can get our data between 5 and 10 kilometers. However, in the Southern Sturgeon greenstone belt, which I was looking, the data is deeper than 8 kilometers and very sparse. So it may not actually provide much help in that area, as opposed to it would in the northeast end of that line. So in my future work, what I want to do is continue to pick more shot gathers. So in this, I said I picked every 10th. It would make sense to pick, to double that, to pick every 5th. That would give me a shot spacing of 250 meters, which would match pretty closely the station spacing of the gravity data, which was 300 meters. I could also evaluate S waves in the future or any other information contained in those records. And in terms of the model space, I can have the gridding when memory becomes available, and that will help refine some of the areas at the top of the model where I'm calculating the statics. And then I would also like to complete the joint inversion of the whole Western Wabigoon as well. And that's it for my talk. Thank you for listening, and I'd be happy to answer any questions you may have on this.
Great, thanks very much, Chris. There are a couple questions in the chat. Does anybody have anything live? So Chris, Richard's put in the question. Would it be worthwhile reprocessing the seismic reflection after you have static corrected the data, or is this just a useful check?
No, I think it actually would be worthwhile to focus the reprocessing of the seismic lines in terms of enhancing reflections in the uppermost 5 kilometers, and doing a really good statics approach through that. So yes, definitely, I do. My plan is to actually try to reprocess the line with this new information.
Okay, very good. He's got another question. With rays going parallel and perpendicular to the Sturgeon line, is it possible to estimate any anisotropy in the seismic velocity?
I think it would be, and I think probably that was the original aim of setting this survey up with this configuration. I hadn't seen any publications that had used the broadside information, but certainly having the different directions of those lines would be very helpful. And I also have the 2D information. I have the results from the 2D imaging. In fact, I had done a bit of work on this a few years ago. And this is just showing, again, the model as collected, looking north-south and then east-west. So there's the 2 lines, and I've kind of cut them in the middle. Evaluating in just in these 2D lines may also be able to help look for any anisotropy in the P or S wave speeds. Hope that answers that question.
All right, very good. And Christian has a question in the chat. Have you looked into auto picking algorithms for first break picks? Is the data too noisy?
I believe that it probably is too noisy. As far as the lithoprobe data goes, the broadside shots and receivers, there's not too many of them. I'm looking at hundreds of traces rather than tens of thousands. So it's not too onerous to pick. But yes, in the metal earth data, there could be a lot of work. And I had tried the auto picking algorithms in Geotomo, and was getting pretty crude results. And I picked manually from 5 kilometers out. When I received the data set, I noticed that it had some auto picking done on it, which was okay, but there were some areas where there was a lot of noise, and the picks were out by hundreds of milliseconds. So in short, yeah, I think it is too noisy, and it has to be picked manually.
Okay, great, thanks, Chris.